Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Claudia de Rham. She's a professor of theoretical physics in the Abdus Salam Center for Theoretical Physics at Imperial College London, with a talk on gravity as an effective field theory. Her research focuses mainly on massive gravity, modified theories of gravity, and also quantum gravity. It's an honor that she's today with us. And please remember to raise your hand if you have any question at any time, and I will leave you with Claudia. Please go ahead.
Thank you. Thank you very much, Daniel. Thank you everyone for being there. Also, thank you ICTP and Physics Latam. You pronounce Latam or Latam? I don't know, but it's great. It's great.
Exactly. Latam.
Latam, okay. Yeah, it's great to be here, even if only remotely, and maybe next time I can be there in person. So today I'll be talking about gravity to start with, general relativity as an effective field theory. So trying to understand how, without having direct access of the high energy completion of everything, of nature, including of quantum gravity, we can still make predictions and we can still try to understand phenomenology at low energy as an effective field description, and then parameterizing a lack of knowledge with operators within the context of a quantum effective field theory. So to start with, I'll try by describing gravity as an effective field theory for a massless spin-to field. And then we'll go through the more standard framework of general relativity plus operator corrections as an effective field theory. So this is, in a nutshell, a little bit the essence of what I'll be discussing about, and I'll derive the quantum field theory from a low energy perspective. Some of the ways I'll introduce them, the results will be similar to what you have probably heard in various different kind of courses, but we'll use slightly different kind of assumptions, and so I think it is useful to set everything in context. So overall, everything I'll be doing is within the idea that ideally we'd like to have access to new layers of physics, and ideally in the not too distant future, we can better understand what is the completion of quantum gravity, whether it's string theory, formal theory, causal sets, loop quantum gravity, or something else. So maybe some of those aspects are related to one another, but without being too explicit about the high energy completion of nature, we'll like to try to make some connection with the ultimate realization and observables to which we have access to with experiments and observations. So whether it is a test of gravity in the solar system, or physics of the standard model and beyond, or currently tests of general relativity through black holes, gravitational waves, and cosmological paradigm, all of this is a new window of opportunity to test and probe the nature all around us, and ideally have access to new layers of physics. So we like to make the connection between the two. So in these lectures, I will build gravity as an effective field theory from the ground up, considering as a low energy effective description for a more fundamental and yet unknown high energy completion. But even though the high energy completion may be yet unknown, it still has to satisfy some specific properties that we can still all agree on, and I'll describe those probably in the second half of those lectures. And so those properties have very specific implications for the kind of corrections that we can build in a low energy effective field theory description in general, and in particular for gravity. So because I think it is useful to understand some of the concepts in a more familiar situation, I'll start with the theory of a spin-one field, a massless spin-one field, which will end up being the theory of a photon, and Maxwell will come out of that. But I think it is useful, even though I know you're all very familiar with that, to derive some of the guidelines of what can be done and how we arrive to Maxwell's theory for a massless spin-one field in any dimensions before we go into gravity, where exactly the same procedure can be followed, and then better understand how we can make connections with a high energy completion. So most of what I'll be talking about today, in fact, is completely generalizable to any number of dimensions. But just for simplicity, to get the dimensions right and for some of the behavior, I'll focus on four-dimensional Lorentzian spacetime most of the time. Sometimes I'll work on Euclidean. I'll let you know when that happens, and I'll be working with mainly plus signature. This is just for convenience, and the same units as I'm hoping you're all used to. So because we're starting with a Lorentzian spacetime, we can assume Lorentzian invariance and locality, even though, of course, the world we live in does spontaneously break Poincaré invariance. There's some strong reasons to believe, based on, for instance, the standard model of particle physics, that fundamentally, if you zoom to the smallest possible distance scales, we should restore some level of Poincaré invariance. So this is my main assumption, in fact, that we're living in a world where in the vacuum, we are in Poincaré invariance. So if we have Lorentz invariance, I can start by defining fields which have some particular representation under the Poincaré group, under the Lorentz group. And in particular, I can start talking about what a notion of spin. So we're not going to go through spin zero because we all know how to write down the theory for a scalar field. This is all well known. Of course, you all well know what the theory for a spin one field is, but let me go through that because the notion of gauge invariance comes out of that, and that's useful for us to understand a bit more precisely. But without talking about gauge invariance to start with, if I have Poincaré invariance, I can define a representation under Lorentz group. So I have a spin one field, which transform in a particular way. I haven't written it there, but I'm sure you all know how it will transform under Poincaré transformation. And I can also define a notion of mass. And so I'll consider to start with a massless spin one field. So this is a well-known representation on Minkowski. Now, assuming locality, and again, this notion of Lorentz invariance, the kinetic term for the spin one field that I can write down can only have specific terms. So I need to have something which is a scalar at the level of the Lagrangian, and that is local. So something which has a kinetic term is quadratic in the spin one field and has two derivatives is something built like that. And I have different ways in which I can contract the indices. So I have this term, that term, and then I have in principle a third possibility. But in this case, in flat Minkowski with no boundaries, this is after integration by parts, just the same as that one. So without any ambiguity, I can set this term to zero and absorb it in there. So now if I consider this kinetic term for what is a massless spin one field, in 4 dimensions, the vector field has a priori 4 degrees of freedom. And we know by Lorentz invariance that those degrees of freedom will have to come in with a kinetic term which is associated with the Lorentz signature. And so one of these degrees of freedom would always have to come in with a negative sign. We can see that easily, for instance, if we take a homogeneous situation where the spatial derivatives are zero, I just focus on the time derivatives, then I have the proper kinetic term for the various components of the vector field. So this is the spatial component of the vector field, the time component of the vector field. And so we see that if we wanted the kinetic term for both the spatial and the time-like component of the vector field to be positive, we would need A1 to be, in fact, this should be negative, and then this one should be A2 plus A1 should be positive. And now I can do the same thing in static situations where I take the time derivative to be zero. And in this case, so this has to be the other way around. In fact, the A1 has to be positive. And sorry about that, this is the wrong way around. And then you can see that the A1 plus A2 has to be negative. So you see that if you want the situation to be stable in both homogeneous and static situations, you in fact see that you can't make that both work. You need to choose signs for the coefficients of your kinetic terms in your Lagrangian, which would be contradicting each other. So that's a quick way to see it, but we can do it in a slightly better way. But first of all, I'd like to explain why the level of the kinetic term itself is so pathological to have a theory which is built out of ghost degrees of freedom. So a ghost, as I introduced it just there, you probably heard of that before, is a degree of freedom which has the wrong sign kinetic term. And by itself, if you just had one single field which had a wrong sign kinetic term, in principle, you can redefine all of your conventions, and as an isolated sector, that would be fine in itself. Rather than having the Hamiltonian being bounded from below, it will be bounded from above, but in principle, that's just a matter of convention. The real issue is if you have a theory, as is the case in the case of a spin-one field, if all the components of the spin-one fields are dynamical, the real issue is if you have multiple degrees of freedom that come in with opposite kinetic term and they interact with one another, because then the opportunity to decrease the kinetic energy of one field can be compensated by that of increasing the kinetic energy of the other field, and that leads to an instability. So this is very different, for instance, from a tachyonic instability. We hear about tachyonic instabilities all the time, and they can be completely physical and under control. For instance, we may think that the Higgs potential underwent a period of tachyonic instability throughout the history of the universe. And in principle, you may even think that the current or the past cosmological evolution of the universe may be a sign of something being driven in time, may be related to a slightly negative slope potential related to a tachyonic instability. So a tachyonic instability is an instability in the potential, in that the second derivative of the potential can be negative. For instance, if you take scalar field, let me just consider a single scalar field here, which in this case has the right sign kinetic term, but then it has the wrong sign mass term. So rather than having, it should be minus the potential. And so that means that the potential goes like minus m squared phi squared. And so you see that you have an unstable direction here. But in that case, the scale of the instability is related to the second derivative of the potential and can be under control. So a tachyonic instability tells you that you're driven towards a new minimum in your potential, and that's really where you should start quantizing your theory. But there's a scale that controls the size of this instability, that controls how fast you are driven towards the new minimum of your potential. And that ability to control the dynamics related to the scale of the instability in a tachyonic instability is very different from a ghost instability. So for instance, here for the tachyonic instability, I can make the slope of the potential, the second derivative of the potential, weak enough so that it's a very well-controlled instability. But in the case of a ghost-like instability, the instability or the scale of the instability is related to the momentum of the field itself. And so in principle, there's no limit to which you can drive in the momentum to be as large as you want, leading to an arbitrarily fast level of instability. There's no other scale in here than the momentum of the field themselves. And so in principle, you can have the momentum of that field being arbitrarily small, compensated by the momentum of that field being arbitrarily large, or vice versa. And so that's really the key difference between having a ghost instability at the level of the kinetic term itself, just in here, as compared to have a ghost-like instability, tachyonic instability. So to better understand why in the case of a massless spin-one field, without doing things slightly differently, we always led to a ghost-like instability, the best is to think about the transverse and longitudinal modes of the spin-one field. So we all know, you all know, of course, that what we will end up recovering from a massless spin-one field is the theory of a photon, Right now we're doing things classically, but then you can do that quantum mechanically as well. And so we'll be driven towards electromagnetism, where the spin one field corresponds to a field traveling at the speed of light in the vacuum. And it has to travel at the speed of light. You have no fluctuations along the line of propagation of the spin one field. We know that this is the result we will end up with, but if we didn't know that to start with, we could think of having the spin one field and split its degrees of freedom along the transverse direction and along the longitudinal direction. So I'm going to write my vector field as a transverse mode, which satisfies the transverse equality. And then I have, in principle, an additional mode, which I'll call longitudinal mode, as I write as the contribution of the vector field, which is along the line of propagation of the vector degree of freedom. And so in principle, if I'm dealing with an arbitrary vector field, and I'm not putting any constraint on the speed to start with, I could have fluctuations along the line of propagation of the vector field, and that corresponds to this longitudinal mode. Now, it is useful to do this decomposition because we will see that all of the pathologies that typically arise for a massless spin one field are captured by this longitudinal mode, and that's why we will need to set it up to project it out to have a consistent theory for a massless spin one field. So we can do that explicitly. I think it's useful, not necessarily for electromagnetism, but it will be useful to understanding where how to go for that for general relativity, in fact, or for a spin two field. So this is the same split I mentioned before. I'm going to split my vector field into a transverse mode, which satisfies this transverse condition. So this is not a gauge fixing term. This is just I just split the degrees of freedom in terms of the transverse part, and then I capture the longitudinal part of the vector field through chi. This is something I can always do in principle. And so that tells me that if I look at the kinetic terms that I had written before, and I focus just on the chi mode, then just for the chi contribution, there's also some mixed mode between chi and A, and then some cross A terms. But let me just focus on the chi term for now. What I have is something which has, in fact, d mu d nu chi, which after integration by parts can correspond to box chi squared. And the coefficient of this box chi squared is A1 plus A2. And so the fact that you have a combination which is A1 plus A2 in here is related to what I mentioned before when we were splitting the behavior of the degrees of freedom in the homogeneous case and in the in the time translation invariant case. It was so that in one case we needed to have A1 plus A2 positive, and in the other case we needed to have A1 plus A2 negative. And so this combination A1 plus A2 seems to be relevant for diagnosing some of the dynamics of the degrees of freedom that we have in the theory. So now for this longitudinal mode, just focusing on this for now, we can see that the equations of motion for this degree of freedom will correspond to box squared acting on chi with an A1 plus A2 in front that I haven't written it down. And so that corresponds to some terms in the equation of motion for the longitudinal mode that carries higher derivatives. It can go all the way up to 4 orders in derivatives. And we know by Anders-Rogatsky theorem that a field that has additional derivatives are in fact related to additional degrees of freedom that always come in with the opposite sign kinetic term. A quick way to see this is for this longitudinal mode chi, the propagator goes like 1 over box squared. So I can read. So I don't have a pen in here. I'm actually doing research at the Parameter Institute, and I didn't take my pen with me. I'm sorry for that. So I can't write down anything. But the let me try. Maybe I can write this. It's gonna be a bit clumsy, maybe. So this I can write it as there's the A1 plus A2 in here, and then I can write it as guys box squared. Sorry about that, box chi with a minus in front of this. So you can see that propagator for the chi field in here is 1 over box squared. And I can always split this 1 over box squared as the difference between two massive propagators. It's the limit when m goes to 0 of one standard kinetic term, propagator, I should say, and then another one which is not only a ghost but also a tachyon together. So it's a ghost and tachyon degree of freedom. You can see that more directly by doing change of a field redefinition. So the equation of motion for the field chi in here, as I mentioned, it corresponds to box chi squared is 0. And so I can, in principle, think of it as introducing what you may think as a Lagrange multiplier, but it's not really a Lagrange multiplier because it doesn't impose a constraint. It actually imposes a dynamical equation. So this is, you should just think of it as a change of variables. So rather than writing box squared chi 0 directly, I write it through the intermediary of another field, chi tilde, and I said box chi tilde is equal to 0. And so those two equations of motion, and they're really two equations of motion, they're not constraints, can be derived from that Lagrangian. Chi tilde box chi minus a half chi tilde squared. And so what you see in here is that while you have recovered now a Lagrangian, which only involves two derivatives, that's good, it corresponds to a kinetic matrix in field space, which is off diagonal. It only has component along the chi tilde chi direction. And so that means that the determinant of this field space kinetic matrix will always be negative, and so there will always going to be one positive and one negative eigenvalue, so they would always come in with the opposite sign kinetic term. We can make that very explicit by diagonalizing this field space kinetic matrix if we wanted to. So if we diagonalize that in the field space, it just corresponds to saying that chi corresponds to a particular combination of two fields, and chi tilde corresponds to the orthogonal combination of the two field. And so this Lagrangian can be written as the kinetic term for phi 1 minus the kinetic term for phi 2, and then some interactions between the two fields. So those two fields have mixing at the level of the mass term with some tachyonic and healthy mass term coming in here, but also have kinetic terms which always come in with the opposite sign. So this is a well-known theorem, the Strogatsky theorem, that tells you that if you have a theory where the kinetic terms comes in directly with higher derivatives, that in fact hides additional degrees of freedom in these higher derivatives, which always come in with opposite sign, and so are always unstable. They always lead to ghost-like instabilities. So in the theory of a massive even or massless spin-1 field, it doesn't matter, I haven't even introduced what the mass for this field would be, but just at the level of the kinetic term for a spin-1 field, we see that we always led to some instability unless we can find a way to make the chi mode disappear altogether, which corresponds to switching off its kinetic term, saying that it's no longer a dynamical degree of freedom. And that's the case if we impose A1 plus A2 is equal to 0. Really, what it tells us is that chi does no longer appear in the Lagrangian for the spin-1 field. And so if we make that split, mu goes to mu t plus d mu chi. I haven't even used the fact that mu t was transverse. Chi should not appear at the level of the Lagrangian for the spin-1 field. And therefore, the Lagrangian should be symmetric under such a shift. In other words, I should have a U1 symmetry to ensure the stability of the spin-1 field. And in fact, this is true at the level of the kinetic term, both for a massive spin-1 field and for a massless spin-1 field. This tells us that the kinetic term for any vector field has to be of the Maxwell structure that has a U1 gauge symmetry. And then in the case of W and Z bosons, for instance, if they have a mass term, then you can include the mass term by hand, which breaks the symmetry afterwards, but the kinetic structure should always satisfy the gauge symmetry. And this is not because we're asking for a theory to satisfy the symmetry as a guiding principle to start with, but rather this is imposed upon us by pure stability considerations. So we have no other choice than having the gauge symmetry at the level of the kinetic term if we want the theory to be stable. And I think this is going to be important for us when we're dealing with spin to field, because we can see that the level of symmetry that we need to have for the theory is not really a choice. The kinetic term tells us directly what that symmetry should be. So let me just erase that if I can, otherwise it's going to be there for the whole duration. Okay. So this is just to summarize what I mentioned so far. If we're dealing with a Lorentz vector field, a mu, or a spin 1 degree of freedom, it's in 4D, but really it's in any dimensions that you want. Assuming locality and Lorentz invariance, the kinetic term for the vector field has to be written in terms of those two things. That's the case in any dimensions that we want. And the kinetic term will be unstable always. It will carry an unstable ghost-like degree of freedom, which is an abruptly fast instability already at the classical level, unless it's invariant under this shift. And it can only be invariant under this shift if those two coefficients A1, A2 are linked to one another through A1 is equal to minus A2. In this case, then the kinetic term will be invariant under that shift, which tells us that the kinetic term enjoys a U1 symmetry, and that U1 symmetry is derived to ensure the stability of the kinetic term of the theory. And so assuming that you have A1 is a minus A2, I then made a convention choice for the overall normalization. That doesn't matter too much. And so what we end up with is nothing other than the Maxwell term, or the Faraday tensor. I don't know how you call this one. I call it you can call it the Faraday or the Maxwell tensor, the field strength for the vector field. And you will cover the electromagnetism theory of Maxwell for if it's a massless spin 1 field. So if you don't start introducing a mass as well. Otherwise, you can introduce a mass, and then you'll see that the kinetic term for the longitudinal mode will come in the mass term of the vector field that you have. Okay, so this is a situation for a spin 1 field. I'm not saying that because I think you're going to be particularly excited about recovering Maxwell theory, but because this is useful for us to understanding how we can, in principle, use the same guiding principle to derive the theory for a spin 2 field, the theory for a graviton at the classical level and at the quantum level, and how you can see that GR emerges from that, from a purely stable field theory perspective, as opposed to coming out from the pillars of general relativity. And I think that's quite nice, because we don't need to start with some of Einstein's principle on covariance, on other kind of equivalence principle to derive general relativity. Is actually much more profound, much more general than that, just requiring for a field theory of a spin 2 field to be stable directly brings you to general relativity without having any of the underlying principles that you may think may to some extent be a little bit more subjective and that you may want to challenge. So we'll do exactly the same thing, and that will build us towards building gravity as an effective field theory from the ground up, and then looking at corrections for that. So I think this is Weinberg in here. I think you probably know by now, but let me just tell you again that we can think of general relativity, in fact, as an effective field theory. In fact, the standard model and general relativity, we can think of them as a leading term in an effective field theory. And so they are just the first operators that come in an infinite series of different operators. And all of these different operators will capture a lack of knowledge from the ultimate high energy completion of everything. Ideally, we would love to being able to resum them all and get up with string theory or whatever alternative there is, but it's of course very, very challenging. So let's start by just thinking about a spin-2 field. Now we'll start with a spin-2 field, which has a representation as a symmetric tensor field in Minkowski. Again, I'm working in 4 dimensions, but it doesn't matter too much. What really matters is being able to have representations of the Poincaré group. And so under Poincaré transformation, I have my coordinate having some Lorentz transformation and some translation. So this is a constant shift of the coordinates, and this is the Lorentz matrix, the Lorentz boost. Then we know that Minkowski metric does not transform under Poincaré transformation, and my spin-2 field is an object that transforms as a rank 2 tensor. So it transforms like this under the Poincaré transformations. And I'll further assume that H mu nu is symmetric under mu and u. So now, assuming exactly the same thing as we did for the spin-1 field, let me just start by writing down what is a possible kinetic structure for my spin-2 field. And I'm not even going to tell you whether it has a mass or not at this stage. I'm not going to assume any symmetry to start with. This is just innocent spin-2 field living in Minkowski, and I may want later on to add a mass or not. I won't, but you may want to. But in terms of the kinetic structure, I have different possibilities to write down. So I'll just write the square of dh, dh, so 2 derivatives on 2 h's in this form. You can write it differently by integration by parts, but this is useful. And in this case, there's only 4 different types of terms that I can write down. You can very easily start writing something which looks a little bit different, but then do integration by parts, and you'll see that it will end up looking like this. And so this is the symmetrized version of those 2 things. So now in principle, there could be for H mu nu in 4 dimensions. If it's a symmetric object, it will have 10 different components. And so in principle, there could be 10 degrees of freedom embedded in this object. Now you know, you all know, I know you all know that ultimately what we will recover from that is general relativity. And I know we all know that in general relativity, the waves associated with the metric, the gravitational waves, can have 2 polarizations. So there's really 2 fundamental degrees of freedom associated in a spin-2 field, massless spin-2 field in 4 dimensions. And so if in principle I can have 10 components or 10 degrees of freedom in that object, we know that this is A too many. And so just to cut a long story short, I think we can understand that this tells us that we will need to emerge from that, the need to have 4 local symmetries, and each local symmetry removes 2 degrees of freedom, so that starting from the 10 degrees of freedom from H mu nu, you remove 4 times 2, you remove 8 degrees of freedom, and you're left with 2 degrees of freedom, which is the right number of degrees of freedom for a massless spin-2 field in 4 dimensions, is the right degrees of freedom for general relativity. So this is a nutshell what we need to derive, because I know you know what the answer should be. Just like in electromagnetism, just like for the spin-1 field, we started with a vector field in 4 dimensions, which has in principle 4 components. So it could have had in principle 4 degrees of freedom. It's really the A0 there, or the longitudinal mode, or the A0, a combination of those 2 things, which is the Gauss-like degree of freedom that we'd like to remove. But in order to remove it, we actually have to have 1 local gauge symmetry, and the local gauge symmetry removes 2 degrees of freedom because it imposes a first-class constraint. The first-class constraint removes in phase space 2 degrees of freedom. And so we're left in, for the spin-1 field, we were left with 4 components minus 1 gauge symmetry that removes 2 degrees of freedom. We were left with the 2 polarization of electromagnetic waves in 4 dimensions, which is the right number of degrees of freedom for electromagnetic waves in 4 dimensions, for a massless spin-1 field in 4 dimensions. Now, it's exactly the same thing for the spin-2 field, only we'll need to have not one local symmetry, but 4 local symmetries instead, each removing 2 degrees of freedom. So we can see that explicitly in the case of the spin-2 field, and we'll do the same split as what we did before. But let me show you a little bit how we can think of those potential components and degrees of freedom more explicitly in the case of spin-2 field. So I know we all know that in general relativity, the standard degrees of freedom that are captured in your h mu nu are the 2 polarization of gravitational waves, which are transverse degrees of freedom. So if I had on the left-hand side in here, if I had a gravitational wave passing straight through your screen, straight through the slide, then they will just lead to modification along the transverse to this line of propagation, so along your screen itself. And this is a side view for gravitational waves going along this direction. They don't do anything, they don't evolve any perturbation along the line of propagation. They just do so along the transverse to the line of propagation. So the gravitational waves that have been detected 10 years ago, almost now, in a month, it'll be 10 years ago, are purely transverse modes. In principle, there could be 4 other degrees of freedom, and if each one of these 4 additional degrees of freedom was ghost-like, there will be an additional degree of freedom riding on them. So sorry, if each one of these 4 degrees of freedom came in with more than 2 derivatives, they will actually hide 2 degrees of freedom in each one of them. And so there would be 8 additional unstable degrees of freedom. So you can see 4 of them there. But in fact, if they are all a Stragatsky kind of instability modes, there's 2 degrees of freedom hidden in each one of them, each one carrying its own potential pathological ghost-like instability. So in principle, they could be, in addition to what we can identify as vector fields from the point of view of linearized Lorentz invariance. So those are modes that do modification across the line of propagation and one of the transverse directions. So one of the transverse direction here and another of the transverse direction there, but also along the line of propagation. So there's 2 degrees of freedom that look like vector modes. And then in addition, there can be something which looks like a conformal mode or the breathing mode. And this is something that people are actually trying to detect with gravitational waves. So it has just along the line transfers to the line of propagation, but it doesn't preserve volume. So it's a slightly different kind of mode that can be present. We'll call it the conformal mode. And then in addition to that, this can be also a purely longitudinal mode, which is just along the line of propagation. And that will be carried by a d nu chi just along the line of propagation. It doesn't do anything along the transverse direction. So that's just symbolically a way to think of the additional 4 components, and each one of them carrying an extra ghost. So we know that if those 4 degrees of freedom were present, and if they carry a ghost with each one of them, they will lead to instabilities. And so we need to find a way to project them out from a kinetic term for the mass, for the spin-2 field. And so we will need to have 4 local symmetries. Again, the best way to see how those come in is to split the spin-2 field through a transverse part and a longitudinal part. And because we're dealing now with a spin-2 field that can be represented as a tensor, as a Lorentz tensor, then we can write this longitudinal part, in fact, as a vector. So it's the derivative of vector. We're just in Minkowski here. So all of this is just partial derivative. And so if I focus just on this 4 longitudinal modes, the kinetic term for these 4 longitudinal modes can be captured through a combination of these different operators. And so there's one term which is box squared chi mu, and another one which is box d mu d alpha xi alpha. And so putting all of this together, we see that the only way to remove all of the higher derivatives that are present in here, so there's 3 derivatives in here, there's 3 derivatives in here, there's 3 derivatives in here, so that will lead to higher derivative equation of motion that carry some Ostrogowski ghost instability, unless we have this coefficient being 0, that coefficient being 0, and this coefficient being 0. And so for this to happen, we need to set some specific choices of coefficient where B1 is minus B2, is B4, is minus B3. And so from that, I'll show you in a second, we'll recover with that choice of coefficient the Liftin-Oritz operator, which is the linearized-Einstein tensor. This will end up being the linearized-Einstein tensor, and I will recover linearized Einstein theory of general relativity. But also it tells us that if we have a theory of a spin-2 field, we need to end up in such a way that h mu nu going to h mu nu plus d mu psi nu, this degree of freedom or this component does not appear in the resulting Lagrangian. And therefore, we need to have the kinetic term itself, the linearized kinetic term for a spin-2 field, independently of whether it's massive or massless, should be invariant under a shift of h mu nu going to h mu nu plus this. And then hopefully this is very reminiscent to something that you know, which is linearized diff invariance. So once again, and sorry, maybe what I said before was you have terms which are quadratic in psi mu, and here those will carry 4 derivatives, and then terms which are linear in psi and cross term with this, and those will carry 3 derivatives. You need all of those to be 0 because all of those would otherwise be higher derivatives. So with that choice of coefficients, which is the only way for all of the higher derivatives to cancel out, there's no other way than that, we do recover the Liftin-Oritz operator, which is linearized general relativity if h mu nu was the linear order term in the metric about Minkowski. So in other words, what we recover from here is h mu nu and then this Liftin-Oritz operator acting on h mu nu, which has this very specific structure. And in fact, is built so that its invariant under h mu nu goes to h mu nu plus d mu psi nu. It's not that we really asked for the symmetry to be there in the first place. It's just that if psi nu did appear at the level of the kinetic term, it would necessarily appear with higher derivatives, and therefore it would carry an Ostrogowski ghost-like instability, and the theory would be unstable. So the only possible theory for a spin-2 field is if the kinetic term itself is in fact invariant under this shift, and so inherits what appears at this level to be a gauge symmetry. Later it's not going to be a gauge symmetry, but it appears to be a gauge symmetry at the level of the kinetic term. And we haven't said anything about all the potential terms, mass term and everything that could in principle themselves break that symmetry, but it doesn't matter. The kinetic term itself has to satisfy this symmetry. And so we see that linearized diff is imposed upon us by stability consideration, and that's it. And it's not even imposed upon us by any other kind of foundational principle as to what we would like observers to see, for instance. So this is not coming to us from any kind of coordinate transformation invariance or equivalence principle considerations to start with. It's much more fundamental than that. It's simply just stability. Okay, so now that we have understood that for the kinetic term of a spin-2 field, we need to have linearized diff invariance to ensure stability. We could, in principle, just think of the spin-2 field and the massless spin-2 field by itself and not interacting with it. That's fine, but then it's a little bit boring because we would not see that spin-2 field. If you want to start interacting with this spin-2 field, the first thing we can do is consider an external current, an external source, T mu nu. So by considering an external source, T mu nu, what I have in mind to start with is something which is not dynamical. So it's just really just a way to probe the theory. It's not really physical because we'll see everything has to be dynamical at the end of the day. But for now, let me just consider an external source. So T mu nu is an external source, which enables me to probe this spin-2 field. In this case, it's just massless. It's a linear spin-2 field. And I'll probe it with this interaction like this. Then if I take the linearized equation of motion, I have what looks like my linearized Einstein tensor in here. That's what it looks like. It's a linearized Einstein-Hilbert term is equal to T mu nu. So this looks very much like the linearized Einstein's equations, although I haven't talked about Einstein, I haven't talked about coordinate invariance or anything like that. And so linearized def tells us that we need, linearized def tells us that if I shift H mu nu by H mu nu plus d mu d nu psi, I should end up having something which is invariant in here and in there. And I can see this happens if this whole contribution here is transverse. And so asking for this contribution here to be transverse, which is identically the case, you can take the transverse part of this and it will give you identically 0, which is nothing other than the Bianchi identity at the linear level, will demand conservation of this external source, external current. And so it's the symmetry that we need to have for the kinetic term at the linear level that demands that if you want to probe the spin-2 field at the linear level, you need to do that with a conserved current, something that satisfies d mu t mu nu is equal to 0. And that, of course, is probably looking very similar to what conservation of the stress energy tensor looks like. But it's just coming from linearized def, and it's not even coming from the Noether charge related to Poincaré invariance. This is just the linear def symmetry, the local symmetry at this stage. So this is the case. This all makes sense if I consider T mu nu here, everywhere, to be an external source. It's just something I impose by hand, and I'm not going to think at the level of the path integral as varying with respect to field, integrated with respect to field, which are present in this T mu nu. But that's not the real world, really. If I wanted to think of something more physical, what I like to probe my spin-2 field with is anything that I have possession with, but in the end, it's going to need to be dynamical degrees of freedom. So just for simplicity, let me just think of what would happen if, in addition to this spin-2 field, I also had a scalar field. That's the simplest thing I can think of, and I like to make them interact with one another. So my scalar field is going to be my way to interact with my spin-2 field, just as the simplest dynamical degree of freedom that I can think of in this case. So if I have the simplest action for a scalar field, I have my kinetic term for the scalar field, and I have a potential for the scalar field or not, it doesn't matter too much. That's the simplest thing I can think of. I know we all know how to derive the stress energy tensor for a scalar field. It's T mu nu given by that. You can derive this from Poincaré invariance, the associated Noether charge associated with that, or you can derive it in different ways. And that seems to all make sense. So now the conservation, the linear, in the sense of linear H mu nu conservation of T mu nu is just the partial conservation of T mu nu. And that, as an equation, tells me that the first term is box phi, d nu phi in here, plus there's another cross term, which is d mu phi, d mu d nu phi in there. And then from here, I'll have the same term again, and then the derivative of the potential d nu phi. And so the conservation of energy, of the stress energy tensor, I should say, in fact tells me that this box phi d nu phi minus v prime d nu phi is 0. But we know that the Klein-Gordon equation for the scalar field, the equation of motion for the scalar field itself, is box phi minus v prime is equal to 0. And so the stress energy tensor itself is necessarily conserved on the Klein-Gordon equation. And so all of this seems to make sense. It's consistent to have the scalar field equation of motion. That's also what imposes the conservation of the stress energy tensor at the partial level, and the conservation of the stress energy tensor at the partial level is what is imposed by the linear Bianchi identity or the linear stiff invariance at the level of the spin 2 kinetic term. So that seems all to be completely consistent. And now that tells us that the naive theory for graviton, you can think of it at the classical level or the quantum level. All of what we do here is really classical, but I could start putting hats on everybody and it'd be all quantum. There's absolutely no issue with doing all of what we're talking about the quantum level as a matter. So the naive theory for a spin-2 field coupled to a scalar field would be, I have my kinetic term for the spin-2 field in here. I have my scalar field Lagrangian in there, the same thing I had in there. And if I vary this with respect to the scalar field, I'll get the Klein-Gordon equation. And I can just try to couple them both as we did before, H mu nu, T mu nu, where now this T mu nu, and I may consider it to be dynamical, is the T mu nu for that scalar field. It's not any T mu nu I want, it's the T mu nu for the scalar field, which is given by that. So now we really have direct interaction between the spin-2 field and the scalar field. There's a cubic interactions, and then maybe more in here, between the spin-2 field and the scalar field. Okay, so that's what we wanted. We're getting what we wanted. But in this case, as said before, when I consider this part here, the equation of motion for the scalar field gives me that Klein-Gordon equation. But if I'm honest with myself, when I have this whole action as my action now, including the interaction between the spin-2 field and the scalar field in here, which is what we wanted, then the equation of motion for my scalar field are no longer just box phi minus v prime is equal to 0, because I need to also vary the contribution from T mu nu in here with respect to the scalar field. So in addition to the part that I like, there's an additional contribution to my scalar field Klein-Gordon equation, which tells us that including that part here, we no longer have that stress energy tensor is conserved. So this interaction between the spin-2 field and the scalar field, which is exactly what we're after, directly breaks the partial conservation of the stress energy tensor of the scalar field. And so we no longer have, in the presence of this term, linearized diff invariance. The symmetry is broken. There's no longer gauge invariance, because when I take H mu nu goes to H mu nu plus d mu d nu phi, this is invariant. This doesn't depend on H mu nu, so we have this. But this, when I switch H mu nu goes to H mu nu plus d mu psi nu, there's a term that will only vanish if after integration by parts, I could have T mu nu is equal to 0. But this is no longer 0 because of the interactions between the two. And so there's a breaking of linear def in this case. And this breaking of linear def tells us that the degrees of freedom, the additional degrees of freedom that were present in H mu nu and that were removed thanks to the linear gauge symmetry that we had in here, are no longer removed in there. And so then they become dynamical, pathological, unstable degrees of freedom. This is something we cannot have. So this theory itself is inconsistent. This theory is pathological and carries ghost-like degrees of freedom, which we cannot live with. So the naive theory of a spin-2 field, graviton coupling into a scalar field, is itself not consistent, because there's a failure conservation of energy at that order. The stress energy tensor that we have in here, if it's built out of the dynamical degrees of freedom phi coming from there, then this is no longer conserved. You will have some modifications to it that goes like h of m Planck, which directly implies that linear diff invariance is broken at the same order. And so the resolution behind that is to supplement the symmetry, the linear diff, with nonlinear correction at the same order. So in principle, we would need to say the symmetry is no longer just this. It has a correction at that order, which enables me, now some of the terms in here will cancel out the new correction that I had in there. But as soon as I include that new interaction, that new component in the symmetry, then I'll see that I'll need to carry this to all orders. So this thing in here will start bringing new terms in here and in there, which will need to be cancelled out order h squared over m Planck squared. So I need to introduce some h squared over m Planck squared correction to that symmetry. And then those ones will introduce new terms which don't satisfy the symmetry at order h cubed over m Planck cube. And so again, I need to introduce another one here, etc., etc. So the resolution to recover a consistent theory where I can couple a spin-2 field, massive or massless, it doesn't matter at all, with any other dynamical degree of freedom, is to promote the gauge symmetry to a fully non-linear one, where rather than having just linear diff, I have an infinite number of corrections, which are derivative operator corrections acting on higher and higher orders in H of M Planck, and then the parameter of the symmetry. And so for the theory to be invariant under this fully nonlinear promotion of the gauge symmetry, it tells us that the interactions themselves should not only be at linear order in H mu nu as we had before, but we're going to need to adapt for the higher order terms coming in here. And so I'm going to need to have quadratic orders and cubic order, etc. So a whole infinite series of interaction between, nonlinear interaction between H and the scalar field. And so similarly for the spin-2 kinetic term, because not only the symmetry is not just that anymore, it has this infinite number of terms to adapt for the failure of the symmetry of this term at the first order here. I'm going to need to introduce a higher order there, and etc., etc. And so I'm going to need to introduce an infinite number of terms in the kinetic term for the spin-2 field itself. And you can think of this as the energy carried by the gravitational field, all of those corrections themselves. Even though a priori that's all we needed, in fact, consistently coupling a spin-2 field with anything else at all directly implies that you need to have something fundamentally very nonlinear and promote your symmetry to a nonlinear one. So it forces to promote what you had as a linear gauge symmetry, h mu nu goes to h mu nu plus d mu d nu psi, to something which is fully nonlinear. And in fact, we know from a group theory point of view that linear diff, this symmetry as a gauge symmetry, only has two nonlinear representations. So this can be embedded in two nonlinear ways. The first one is trivial case of the nonlinear situation, which is the linear one. Either you recover, you just decide to keep it completely linear. This is a consistent symmetry in itself, but you know that if you want to maintain the linear symmetry, then the only possibility is for your spin-2 field not to interact with any other dynamical degree of freedom. So you have a non-interacting theory in this case. It's a completely isolated decoupled sector. And so the H mu nu in here cannot be gravity. And so that's completely consistent in itself, but it's very boring because it's completely decoupled for anything we would ever be able to interact with. If we ever want to be interacting with the H mu nu being present in here, you need to rely on the other nonlinear representation of the linear diff, which is fully nonlinear diffeomorphism invariance, which is also called full covariance or full coordinate transformation invariance, where this H mu nu is actually just the linear part in a metric, And this parameter of the transformation is the linear parameter in a full coordinate transformation invariance in this form in that. So showing how you recover fully nonlinear diff out of this and fully nonlinear GR out of the expansion order by order of all of the possible terms at the linear level is something which in principle, in spirit, has been, the spirit of it has been proven by Dazer, also by Weinberg, and you can find some of this in the Feynman lecture. But no one does it fully non-linearly. It's really just the spirit of the method that is being proven in those papers. Particularly, you can go back to, it wasn't shown in that paper, but Stanley Dazer rewrote it in that paper that you can access to. So I highly encourage you to have a look at that paper. And then Weinberg as well showed this some 60 years ago now. That's quite some time. Okay, so if we add the restriction that the action only contains at most two derivatives, the only solution for coupling a spin-2 field, irrespectively of whether it's massive or massless, in fact, is a unique solution, which is general relativity, where the kinetic term that we wrote before has a fully nonlinear embedding, which ends up being the full Einstein-Hilbert term. And you can see that what you had before, H, Lipschitz rate operator H is actually the quadratic term of the full Einstein-Hilbert term in there. The scalar, and then you couple the scalar field covariantly with the metric, where the metric, the H mu nu is written in terms of the metric in this form. And this doesn't need to be a linear decomposition. Now, this is fully non-linear. No one is saying that H mu nu has to be small or anything like that. This is fully non-linear. And you can see that the linear gauge symmetry H mu nu goes to H mu nu plus d mu psi nu extend to full non-linear diff invariance or covariance, where you can think of H mu nu in here being built in there, transforms in that particular way. And so now if you make the assumption that you are working at the linear level, then you will recover this symmetry, but this is fully nonlinear in itself. But you can still think of H mu nu as the degree of freedom for the spin-2 field, and no one tells you that this has to be a linear theory in anything. H mu nu has to be small. And then phi now also has to transform in a particular way under this coordinate transformation invariance, and in this case, it has to transform as a scalar field. But of course, you know how this works out for any other field that you want to. So from an effective field theory point of view, we can in principle add an infinite number of derivative operators and cosmological, and also a cosmological constant, which would be a lower dimension operator to this theory. But it doesn't change the fact that in order to ensure for the theory not to carry any Ostrogatsky pathological degree of freedom, you need to have the symmetry, in this case, full covariance, imposed upon you as a consequence. And so it's the opposite way of thinking as compared to what Einstein came up with when deriving Einstein theory of general relativity, where he came up with covariance as a pillar of general relativity upon which was built a theory. And here is the other way around. We're just asking for a field theory to be consistent in Minkowski. And if we want to couple it consistently in a stable way to a dynamical degree of freedom, then we have to promote the linear gauge symmetry into full covariance. And so we led to general relativity as the unique possibility as an outcome. So let me just do a summary of what we had so far, and then I think it'll be a good time to go for a break. So everything we have done so far was purely classical. And what we have done is recover general relativity as a unique classical field theory for a local and Lorentz invariant massless spin-2 field. So it's massless because we haven't introduced a mass for the spin-2 field. In principle, we could, and that's a whole different story that we could go into. But even if we wanted to introduce a mass term for the spin-2 field, it doesn't change the fact that this structure is completely locked. And we can't do anything about that. And the kinetic term and the interaction between the spin-to field and external dynamical degree of freedom have to be within the context of particular symmetry, which has to be fully nonlinear diff invariance or covariance. And you can't change that. You can't break the symmetry at that level. Of course, we know that UR is a non-renormalizable theory. And so this will not be the full answer of the theory itself, but we can add some operators, and that's what we're going to be doing in the next part, which will still enable us to make predictive classical and quantum calculation at sufficiently low energy for gravity. And I highly encourage you as well to have a look at these beautiful reviews on general relativity as an effective field theory. So this is about the concept of effective field theory by Cliff Burgess, and this by John Donahue, really about general relativity as an effective field theory. Now, even though, let me just say that very quickly before we actually go through building the effective field theory of gravity more generically, even though everything we have done is completely classical, and even though we know that general relativity in itself is a non-renormalizable theory, I'm not going to go through proving that, but I'm sure you all know that, it doesn't mean that we cannot think of everything we have done as a quantum effective field theory. And there's absolutely no issue with thinking about general relativity as a quantum effective field theory, where this h mu nu degree of freedom that we're dealing with can be a quantum, there's no other choice than that, in fact, is a quantum field, which has to be quantum. And in fact, even though, you probably, that's quite some years ago now, that's 12 years ago, for those of you that remember that, probably you were quite young then, when the biceps results came out in 2014, I believe it was, they believed that, well, B-mode polarization were detected, that there's no question about that. At the time, it was thought that these B-mode polarization were a sign, in fact, of primordial gravitational waves. So the fact that B-mode polarization in the sky have been detected, there's no controversy in that, is whether those are a sign of dust or whether they are a sign of primordial gravitational waves, which was proven later on not to be the case. But there was absolutely no issue in thinking of detecting B-mode polarization, which would have been linked to primordial gravitational waves. And those primordial gravitational waves were, in fact, gravitational waves which were produced by quantum fluctuations at the very beginning of the universe. And so the spin-2 field that we're dealing with, the gravitational waves that we're dealing with, there's absolutely no issue of thinking of it as a quantized field. And people do that on a daily basis when they do cosmology in thinking of the quantum implication of the spin-2 field. So this is just to say that there's absolutely no controversy in thinking of gravity as a quantum field theory and in quantizing the spin-2 field. The real issue is to thinking of what happens for a theory of quantum gravity when we're thinking in environments or situations or experiments which are at very high energy scales, close to the Planck scale itself. But if you're thinking of it as sufficiently low energy, you can think of general relativity as a theory of a quantum spin-2 field and look at the implications of the quantum spin-2 field, and that has some predictive implications. And let me, yes. And I'll stop here, and then I'll go through building the effective field theory for general relativity in a second. After the break. So I think we can have a break now. Okay. Sorry, let me just see, because yeah, it's fine. Field theory. So just a few guiding principles in how we're going to build an effective field theory. So first of all, we want to preserve unitarity. That's going to be one of the main guiding principles. And I think no matter what the high energy completion of quantum gravity and of everything is, we like physics to come up as a unitary process. And so that will mean that we want throughout all energy scales, physics to be represented by a unitary theory. And so that tells us that we would like the Hamiltonian to be Hermitian. And therefore, we're going to start with a Lagrangian, which is real. Then we're going to be considering processes at energy smaller than a particular, let's call it a cutoff, or an energy scale, let's call it capital M. And so conservation of energy means that we cannot produce classical states of heavy particle beyond that scale. Of course, virtually, the heavy particles can exist for a small enough period of time, virtually at least in loops, so long as the scale involved are suppressed as compared to the scale M. And so that means that if you consider a low energy effective field theory as an expansion, it should be as an expansion of powers or for momenta, which are suppressed by the scale M, capital M, which is a scale above which we're not considering to produce physical degrees of freedom. So we'll organize our low energy effective field theory as an expansion in powers of derivatives of the scale at which we're interested in. So naively, the correction can never be too large within the regime of validity of the low energy effective field theory. However, we can have in our effective field description for gravity, and I'll show that explicitly, some terms which could be higher derivatives, higher order in derivatives. And this is very different as compared to having higher derivatives directly at the level of the kinetic terms, where there was no way to tame down those Ostrogatsky instabilities associated with this. Now, when we're dealing with higher order operators, which are suppressed by the cutoff of the effective field theory, we consider them to be perturbative. We consider them to be small as compared to the lower order operators. And so even if they come with higher derivatives, we can treat them perturbatively, and they can't give us pathological degrees of freedom. In particular, the Ostrogatsky ghost that would be related to those higher derivative operators in the perturbative sense will come in at the scale of the cutoff of the effective field theory, and so by definition are beyond the regime of validity of the effective field theory in which we describe it. And it's not the case that those degrees of freedom, Ostrogatsky-like degrees of freedom associated with these higher derivative terms are one-to-one associated with the additional degrees of freedom that would come into high energy scales in whatever degrees of freedom comes in there. Rather, they just signal the breaking of the perturbative expansion from a low energy perspective, and then as we go to high energy scales, all the degrees of freedom will come in, but there's not a direct correspondence between the two. So what we want to do now is more directly linked to what we had before, and we'll use the symmetries that we derived all the way to now as guiding principles for how we're going to build our effective field theory of gravity. So we have an ultimate completion of everything that we all know and love, or we would love to know, and then we will love it, which can be at the Planck scale or slightly below the Planck scale, or string scale or something like that, which we don't have direct access to. Today, we do experiment on cosmological scales, which can be all the way down to 10 to the minus 32 electron volt, all the way up to we have probes from what happens at LHC at the order of TeV, and then we even have information from gamma ray bursts, which are very high energy scales. But all of this, all the way up to what we consider gamma ray burst, for instance, this is still within the framework of a low energy description of gravity, a low energy description of everything, which we can treat as general relativity plus potential IR modifications of gravity in a perturbative sense, which capture the imprints of high energy physics on a low energy description. And so all of the heavy modes that come in from the scale M. So I apologize for that. Sometimes I call it little m, sometimes capital M, but it's the same scale. So all the way from that scale M to the Planck scale and beyond, whatever is the representation there. And you don't even need to represent things through fields up to some scale. It can be a different representation. But so long as I can think of a quantum probabilistic amplitude, I'll be able to infer all of this physics into imprints on our low energy effective field theory. And so that then we can use those low energy effective field theory to make comparison with what happens in the solar system, what happens for gravitation waves, what happens for bending of light around a black hole or anything like this. So the high energy theory will involve gravity, and up to some scale may involve some light and heavy modes, psi, but beyond that, it can be the case that I can't even write down a path integral for what I want to describe, or maybe I should only think about amplitude. It doesn't matter too much. But as again, in principle, what we want to do is integrate out all of the physics that happens at high energy and derive the implication for our low energy description of gravity, which is valid below the scale M of the heavy fields we have integrated upon. And so the picture is that, in principle, when you're probing gravity, for instance, you can probe for a sufficient small period of time and space some effect from the imprints from heavy modes, and those modes can be an infinite tower of high spins that can come up at loop level or whatever it is. I don't really want to know too much of the details, but all of those dynamics of the high energy physics is imprinted upon corrections in our low energy effective field theory, so higher order operators in a low energy effective field theory. So we have a low energy effective field theory of gravity valid below the scale M of the field we have integrated upon, plus all the light degrees of freedom, which can be the photon and maybe all the fields of the standard model as well, depending on the scale in which we're working with. So a little bit more explicitly, but not too explicit either, if you did have a path integral up to some scale, it will involve an action, which is that of gravity, some heavy modes, and also some light modes, for instance, photons, and possibly all the fields of the standard model. And you integrate out of all the heavy modes to lead to an effective action at low energy. And that's literally just the integration of all the heavy modes. You may integrate at tree level, you may integrate out at loop level. So the effect that you would have as your EFT at low energy will depend on the kind of UV completions you have in mind. Maybe it's easier and harder to some extent to think about completions with higher spins. So it's easier if you're thinking of higher spin implications to some extent, because then they can already start contributing at tree level. And their effect at tree level is the one that dominates it. So to some extent is simpler, but of course then you're dealing with an infinite tower of higher spin. And if you do that, the effect of all of those higher spin tower on the low energy effective field theory will be an expansion in terms of operators. These are just symbolic corrections, but they have to be local, they have to be real, and they have to satisfy the same level of symmetry as we had for the first term. So they have to be covariant. So they're built out really of the Riemann curvature and covariant derivative of the curvature, and they each suppressed by the mass of the lightest massive higher spin upon which you have integrated out. But that's the only thing that they are suppressed upon, and you have an overall power of m Planck squared in front. Now, that's not the only way you could actually have imprints of your high energy physics on your low energy effective field theory. You also have, for instance, if you're working at energy scales below just the electron mass or the Higgs mass, at energy scales below that, you'll have loops from these massive fields of spin less than 2 that will contribute. At tree level, they don't change the structure of gravity, so they don't contribute, but at loop level, they do. If you want, when you're thinking of even a lower spin field at loop level, it does corresponds to, at the loop level, to a whole superposition of higher multipoles, and therefore they effectively look like contribution from a higher spin, but they come in at the loop level. And so when those fields come in, and they are suppressed directly by the mass of the field that you integrated upon without the Planck scale in front. And so the effect of these loops is suppressed as compared to the effect of the higher spin. So if it was the case that at a particular mass scale, you would have both higher spin coming in and lower spin, scalar field and vector field and fermions coming in, the effect of the higher spin, because they come in at tree level, will be enhanced as compared to the effect of the loops of the lower spin if they came in at the same mass. But of course, that's also not expected. We would have expected to have the standard model, which comes in already with lower spin fields, and you have corrections from the lower models probably captured by fields which are not higher spin states. And only when you start working at very, very high energy scale, maybe there will be the onset of a tower of higher spin states, but those can potentially come in at a much higher energy scale as compared to the lower spin states. So in practice, it's not entirely clear cut as to where the first correction would come in necessarily, if they come in from loops of lower spin or tree level contribution from higher spin. So in principle, we need to consider both approaches, and depending on the situation, one is more relevant than another. So that's the idea overall. And because we're considering the effective field theory, in principle, we need to include all of the operators that are local, that are real, and are consistent with the symmetry in which we were working with. And so it's all sorts of corrections built out of scalar contraction of the Riemann curvature and derivatives of the Riemann curvature up to the field redefinition. Now, if we were to consider, and some people do that, I do that sometimes, maybe you're interested in that, if you want to consider solutions in the vacuum, the black hole solutions, then really the relevant terms, not those ones, the Gas-Bonnet terms doesn't come in 4 dimensions, and then those ones can be removed by further definition. So the first one that comes in is the Riemann cube term, and then you have a Riemann to the 4 term. And here I'm being as optimistic as possible, and so thinking that the lowest possible scale at which they could come in is as if they were coming in at tree level. Really, that would correspond to having higher spin states, and so they're enhanced by the Planck scale in front of it. And so from a low energy effective field theory point of view, if we consider vacuum solutions, operator corrections to GRs and effective field theory, those are the type of correction we should be thinking about. And anything else is really low energy modification of gravity itself. So you can, of course, start including new degrees of freedom in gravity or how it interacts with the matter sector, but that's generally low energy IR modification of gravity, as opposed to the imprint of high energy physics on our low energy effective field theory. And those are two quite different phenomena. In particular, one is perturbative. Those are perturbative and are only looking at those corrections up to the scale M. And when those starts becoming large, I have to stop. In particular, I shouldn't be worried by the higher derivatives that comes in here. Whereas the low energy modification of gravity, they are coming in with their own low energy degrees of freedom that can sometimes have then their own very non-trivial, non-linear realization. And that's not something I'll be dealing with in here. So let me talk a little bit about the higher derivatives operators, because I think this is important, and it is very important in understanding why they are okay in here and how we should treat them in here as compared to when those come in directly at the level of the IR theory in itself and degrees of freedom of the IR theory in itself. So long as we treat them as perturbatively, they do no harm. we can deal with it at the level of gravity itself. It's a bit simpler if I just show you symbolically how to think about it at the level of a scalar field theory, but the same philosophy works out perfectly for gravity. We can do that. That's no issue at all. But it's a little bit simpler to think of it within the context of a scalar field theory. So let me imagine the equivalent of this is the kinetic term, the equivalent of that is the mass term, and then in principle, the equivalent of all of those operators that come in that look at the effect of high energy physics on my low energy effective field theory is captured by all of the local, real, and scalar terms that I can write down. In fact, in here, if I consider a shift symmetric, phi goes to phi plus a constant theory, then the operators I can write down are those ones. They satisfy shift symmetry as well. And I'm just writing them down as a perturbative expansion in powers of derivatives over the cutoff, m. And so I stop at a given order, and I can keep continuing. So there's different kind of operators in there, and how we're going to treat them depends a bit on them. The first thing is any operator which has a box in it can be removed directly, covariantly, by a Fourier definition. And this is because for that theory, at lower order in the equation of motion, it satisfies box from here is 0, or box is equal to the source. And so with the corrections from those ones, the equation of motion at box is of the order of 1 of m squared with derivatives in here. So that means that we can remove all of those by Fourier definition. For instance, for this particular example, if I shift phi to phi tilde minus box phi tilde of m squared in here, and then a half to absorb this one, then from the kinetic term there, I'll have the same kinetic term for phi tilde, and then the cross term will give me minus a box phi tilde squared of m squared, which will cancel that directly. And the other cross term will give me this one, which will cancel that directly. So by a trivial Fourier definition, we can always remove any operator that goes like box phi. And that we can understand very easily at the level of the amplitude. If I have an operator that goes like box phi at the level of the amplitude, then the contribution it will give us is something that goes like p squared, but for a massless field, which is the case in here, the p squared can be traded by m squared, and so by 0, and so it wouldn't give us any contribution to the amplitude. None of this gives us any contribution to the amplitude, which is the physical thing at the end of the day. And if it was massive, I could trade those by lower order operators as well. So this could be traded by m squared, which is also what we would have got at the level of the amplitude. So that means that all of those operators can just be removed by trivial Fourier definition. They're not really physical. They don't give us anything very much. And now we can do covariantly even. And we can do that for gravity as well. So anything in the effective field theory of gravity that involves the Einstein tensor itself, in contractions of the Einstein tensor itself with anything else, and that includes, of course, then the scalar curvature, can be trivially removed by Fourier definition, and we don't need to think about it. So that's why it's really the Riemann terms that are relevant for the effective field theory, the non-trivial effective field theory of gravity. Now, there are other operators of this form, for instance, which are physical, and they will lead to non-trivial contribution to the amplitude. This is lower derivatives, so even it can stay. And then we have other operators of this form, which are higher derivatives, and I can't completely remove by Fourier definition. So there's part of it which is physical, and that leads to non-trivial contribution, for instance, at the level of the amplitude. However, we shouldn't worry about the presence of higher time derivatives, higher derivatives in there. That's not the relevant part. And in fact, the higher time derivatives in here can be themselves removed this time, not by a covariant Fourier definition, but still by a Fourier definition nonetheless, so long as we treat that perturbatively. So in here, just for simplicity, let me take a 2D example, just because I don't want to write things till the end of time. So this d mu phi cube term involves terms which are second time derivatives cube, and then second time derivative squared, second time derivative, and just spatial derivatives. And you could do that in any dimensions, but let me just do it in 2 dimensions, keeping the same mass scale in front. And so from here, we see that that term here and that term there will lead to equations of motion, which are higher order in time derivative, both those terms, in fact. But we can remove them by Fourier definition. In this case, if I shift phi by something which is not fully covariant, but adapts for the time and space split, so I'm going to shift it by something which involves 2 time derivatives squared and that, so this thing and that thing. And then higher order operators, higher order contribution in the Fourier definition. Then from the kinetic term itself, I'll end up with the same kinetic term, and then this term there, which will give me something which is generally second order in time derivatives, and anything else is pushed to higher order, which I can still remove with higher order Fourier definition. And now this box phi here can be further removed by Fourier definitions. So in fact, I don't need to worry about those higher derivatives so long as we can treat them perturbatively, and we can keep doing that, which really means that we're not gonna rely on, for instance, solutions where those higher derivatives are non-trivial and bring you out to new branches of solution which are not connected with the perturbative branch of solution associated with the trivial one with that vacuum there. We're not allowed to do that, because in order to do that, we will really excite this operator beyond its regime of validity. But so long as we treat that perturbatively, we can bring the higher derivatives to higher order, and that means that this is never excites the ghost-like pathologies which would be present in them. So with that in mind, let me go through writing down a little bit more concretely our low energy effective field theory. So as I mentioned before, we start in the UV with a theory that has gravity, that has heavy field, and that has light fields. In principle, we have gravity at high energy. We have the low energy contribution, so the light fields, for instance, the photon in there. And then we have a correction with a high field, and the light field can come in there as well. That doesn't matter too much. And we have counter terms at high energy in the high energy UV theory, which may involves the UV cosmological constant, some coupling constant for the scalar curvature term, and a scalar curvature term, for the Einstein-Hilbert term, and then all of the other terms as well. And now what we'll do is integrate out the heavy modes to be led with a low energy effective field theory that involves a new cosmological constant. It involves a new Einstein-Hilbert term, a new coupling constant in terms of the Einstein-Hilbert term, in front of the Einstein-Hilbert term, the low energy degrees of freedom, and then some new coupling constant in terms of the higher order operators that come in. And so it's simpler to start thinking about those ones. For instance, the IR coupling constant correspond to the UV coupling constant that we had, plus some flow from the UV to the IR, which is captured through this extra term in there. And that's really coming from the integration out of all of the modes from high energy to low energy. And in principle, if we integrated out n fields from the UV to the IR, then the contribution to these terms there will scale like the number of fields that we have integrated out. And that's in fact the case for these terms which are marginal, which are square in the curvature, in the Riemann curvature. They will scale like the number of fields that we have integrated out. For the effective Planck scale in here, it scales also like the number of fields that we integrate out. So if it were the case, for instance, that we integrate out n field at the mass m, then the new Planck scale that we had at low energy is related to the Planck scale that we have at high energy, plus the number of fields times the mass of those fields. And that gives us directly the species bound, which tells us that the number of fields related to a given mass m can never be too large, otherwise their contribution to the low energy Planck scale that we do observe. This is actually what we do experiment with, what we probe the solar system with, what we probe when we're dropping an apple on Earth is the Planck scale here related to the Newton constant. And so that cannot be too large. And so we need to have the species bound where we can't have too many fields related to a given mass m. That's related to the fundamental Planck scale or the fundamental cutoff of quantum gravity, which is that scale in there. And so that's a completely generic band that we always have. Now let me go into the cosmological constant as well, and I'll talk a little bit about this coupling constant for the other fields. So I'll discuss, and I'll finish probably here for today, what the flow to the cosmological constant is. But let me just say that for some of the Wilsonian coefficients, the flow part, so this delta here, this delta there, and the delta that comes in here, from the UV to the IR, may depend on the spin of the field we integrate out. So you probably know that this is the case, for instance, for the cosmological constant. The flow to the cosmological constant, the contribution of the field we integrate out to the IR, the cosmological constant we may observe, depend on the spin of the field we integrate out. So it will give you a positive contribution for boson and a negative contribution for fermions. And that's why if you have a completely supersymmetric theory, the contribution to the cosmological constant will be exactly zero. There's a case as well for some other operators. So for instance, for the Riemann cube term, the contribution from bosons and fermions come in always with a negative opposite sign. And so in supersymmetric UV realizations, the flow to the cosmological constant and the flow to the Riemann cube term are zero. And so in supersymmetric string theory, for instance, the Riemann cube term operator is exactly zero. There's no contribution to the Riemann cube term. However, in bosonic string theory, there is a positive flow to the Riemann cube term, and so this term is always positive in bosonic string theory. So for some other quantities, including that one as well, we can prove that they, independently of the spin of the particle that you integrate out for any field content, and it doesn't even need to be a field, just by unitarity, you can prove that the flow from the UV to the IR should always be positive, and in fact positive definite if there's any interactions at all. And that's, for instance, the case for the Weyl square term, which is a combination of the Ricci square and the Riemann square term. The contribution to this particular contribution, which is the Weyl term, is always positive. And so is the case for the another one of the combination of the Ricci, Riemann, and scalar curvature term is always positive. And that we can prove just by unitarity by looking at the contribution. In this case, we do it at the level of dispersion relation from the UV to the IR is always positive. That does not mean necessarily that the IR imprint of it is positive, because you may have started with something which is sufficiently negative at high energy, so that even though the flow from high energy to low energy is positive, is not sufficient to compensate the initial starting point. But in principle, one would expect in some cases that this is suppressed as compared to the effect of the massive field that you integrate out along the way. Because as you are in the IR, you would expect to be dominated by the lightest massive field that you have integrated out. So for instance, at the LHC, we don't expect to measure directly something related to quantum gravity. We expect the main contribution to whatever will be the first sign of new physics at the LHC to come in from the next massive particles beyond the standard model, and not from something which is very high energy scale. So we would expect this to be very suppressed as compared to that. And that's why we would expect ultimately the IR quantities, at least for those ones, to be positive. But this is not something that we can in principle prove. And in some cases, we can see that it has to be the case that this is so negative that it's not sufficient to compensate the positivity of the flow from the UV to the IR, because we do measure things at low energy which are in fact negative, even though the flow was positive. So let me look a little bit more precisely on how we can integrate out contributions from massive fields. And let me do that from a scalar field contribution because it's easier, but in principle, we can do that from any higher spin even. It doesn't matter too much. So let me imagine that my heavy field now is just a scalar field, and I'm not going to consider any light field. I can, of course, but I'm not going to do that. And so I'm going to look at the interactions between gravity, which is embedded in here. Oh, there's an atom here, which disappeared. I'm sorry about that. Of course, there's an atom here. And then there's further interactions between the scalar field and gravity embedded in here, and then here, and that. And so that scalar field can lead to loops that involve corrections to my low energy effective field theory. In principle, for instance, I have a scalar loop just for the 1-point function for my graviton and for my 2-point function of this formula there. And I could carry on for any n-point function. I can look at the one loop contribution from this massive scalar field. I can do that in a non-covariant way, as we do it like this. In a second, I'll do it in a covariant way, which will be much easier. So for each one of those n-point function, the A1, the A2, etc., I can compute the contribution from the loop of the massive scalar field. This is what it gives me here for this particular stress energy tensor. And then I'm just doing that symbolically for the one loop here for the 2-point function. So you have contribution which comes in from the kinetic term of the scalar field, and then the mass term, and it comes from 2 vertices in here. So you can go terms that goes like m to the 4 or m squared, p squared, where p can be the external momenta, or p to the 4, and then you have the loops of the scalar field. So this is all symbolic. And if I do now dimensional regularization, I'm not going to put the cutoff of the scalar field because this is something which will be dependent on a much more ambiguous way, but I can always do that in a dimension regularization way. And so what I end up with this is a contribution to the 1-point function of a graviton that scales like the mass of the field I have integrated out. And in the case of a scalar field, it gives me a positive contribution to the 1-point function, which is in fact a contribution that goes like the mass of the scalar field to the power 4, and then this trace of h mu nu over m Planck, which I can actually read as the first term in the cosmological constant. So this will repackage with corrections that come in from the 2-point function that will now also scale in the reg like the mass of the scalar field to the 4, and then a contribution that goes like h of m Planck squared. And so this, together with that, and together with all the sum up to all orders in H, corresponds to our renormalization of the cosmological constant. And then from here, we'll also have additional corrections that scale like 2 powers of the external momenta, and that corresponds to a renormalization of m Planck squared r, as we've seen before. And in that case, we also have from the p to the 4 here, corrections to that scale like 4 derivatives, and then 2h, and that corresponds to renormalization of r squared, Ricci squared, and then Riemann squared terms, which in 4 dimensions is just a total derivative. So we could do that perturbatively, order by order. And as we do that, we start with something which is completely covariant. We don't break covariance, but we write it in a way which is not implicit. The covariance is not explicit in this way of writing it down. We can compute every n-point function, and by covariance, it has to be the case, but you can check that as well, that you repackage into contributions which are completely covariant per se, and that's automatic in dimension regularization. We don't need to do it like this, but that's one very quick way to do it. If you want to be a little bit more rigorous, what you can do is instead do the one loop integration of the scalar loop directly. So for this, let me work at the Euclidean formalism for now, just for simplicity for a second. It will just help me with doing the integration, and we can go back to Euclidean. So if I want, for instance, to look at the effect of the cosmological, the effect of the scalar loops into the one loop effective field action for renormalization of the cosmological constant. So we'll have contribution from this, and then all sorts of things that I haven't written down. I can do that integration directly at the leading order term by doing perturbatively a look at the second derivative of the action with respect to the massive field. And then this is quadratic in the massive field. So I can do this Gaussian integral directly. And the answer is well known. You've probably seen it already in the context of any effective field action. Maybe not in the context of gravity, but you can do that. And it gives you the Coleman-Weinberg effective action, where the effective action, so it's in exponentials. When you put it down for the exponential, you get the log of the determinant of this operator. So the determinant of the second derivative of the action with respect to the field, and that you can write down as a trace of the log of that field. And all we need to do is compute this trace of the log. The trace in here is in the Hilbert space, so we can do it by going to Fourier space, and that trace really corresponds to the integration of all momenta of the log of the second derivative of the action with respect to the field. So that corresponds to the kinetic term for the scalar field. This is the kinetic term for the scalar field plus the mass term that you have in here. And now it's easier. That's why one of the reasons it's also easier to do it in Euclidean. We can do this integration in many different ways, but one way to do it is simply to change variable. I'm gonna diagonalize this kinetic term to absorb the metric. So I'm gonna work in Fourier space rescale so that this norm is actually the trivial norm in flat Euclidean space. And in doing that change of variable, we absorb the magnitude, we absorb that measure into the measure, and we end up from the measure of d4k with the square root of the Jacobian. And so this is where the square root of the determinant of the metric comes in. In this case, it's an Euclidean, but you can do it in Lorentzian after that, or you can weak rotate if you want to. And so putting all of this together, the effective one loop action in the case where you can work with small derivatives of the scalar field. So that's in the limit where the external momentum are small. So this is a leading contribution in the effective action for the lowest order operator. You end up with the square root of the determinant of the metric, and then a whole integration here, which in dim red can only take the scale of the mass of the scalar field over which you're integrating out. So by dimension, this has to scale like the mass capital M to the power 4, and then all the rest is just part of the integrations. And that's the flow from the renormalization scale that you introduce. So that tells you the integration of matter loops, no matter what those loops are, will always scale like the mass of these matter loops to the power of this matter field to the power 4 times the square root of the determinant, and then you have the flow in here. And that is the origin of the cosmological constant problem. You always end up with a flow that runs like the mass of the field over which you're integrating out. And so the cosmological constant problem is already a problem with known particles of the standard model. Already from the electron mass itself, you have a contribution to the cosmological constant in one loop effective action that scales like the mass of the electron to the 4, and similarly for the Higgs field itself. So beyond the standard model, it can be that you may have supersymmetry beyond the standard model, and it would be then in such a way that the contribution from every fermion and every boson to the effective cosmological constant at the scale of the standard model, or TV scale, for instance, when you flow from the IR, from the UV to the IR, would give you exactly 0 contribution from all the loops beyond the standard model.
But we know that SUSY is broken within the framework in which we work here. We know that SUSY is broken within the standard model. And so just from the loops of the Higgs field, we already know that we should have a contribution to the one loop effective action to the cosmological constant that should scale like the mass of the Higgs to the power of 4. And so already from known particles of the standard models that we do know do break supersymmetry, we already have a contribution to the cosmological constant, which is of the order of 100 giga electron volt to the power of 4, which is 56 orders of magnitude larger than the effective scale of dark energy, or the effective scale of the cosmological constant observed to explain the Latam acceleration of the universe. So the cosmological constant problem is not a problem with quantum gravity and with what happened at very high energy scale. All of this may cancel out. You may or may not have supersymmetry beyond the standard model, and that may or may not make the problem even worse. But just from the onset of the Higgs mass all the way down to lower scale, we know that we have contributions to the cosmological constant through those one loop integrations, which is already 56 orders of magnitude too large. It's only if you imagine that you had contributions beyond the standard models with massive fields that have a mass that go all the way up to the Planck scale that you may end up with a contribution to the cosmological constant, which scales like the Planck scale to the power of 4, that you end up with a cosmological constant problem, which is 120 or 124 orders of magnitude discrepancy. So, but there's no reason at the current stage to believe this is necessarily the case, because we haven't observed anything beyond the standard model anyways. And if we do, it may come up in a supersymmetric way, or it may come up in a particular way that counts all the contributions to the loops at this level. What we do know is that there's a 56 orders of magnitude discrepancy so far. So I think I'm running out of time. Let me, perhaps I can stop here. Let me see. The rest of what I wanted to do is to look at effect on the imprint of these different type of operators on gravitational waves, on black hole physics, and how to segregate between those using causality requirement. But I don't think I have much time left, so maybe I'll just let me just say this slide, which I think is quite interesting, and then I'll stop here. So for the effective field theory of gravity, the cosmological constant problem is the real elephant in the room, which hasn't been addressed. We're waiting for you to address it. But let me park that on the side for now. And so if I forget about the cosmological constant problem and I assume it'll be resolved in one way or another, then if I consider solutions in the vacuum, the relevant operators that I need to worry about are the dimension 6 operator, the Riemann cube operator, which is only present if the realization is non-supersymmetric. So, for instance, in bosonic string theory, but otherwise in supersymmetric string theory, that wouldn't be present. It can still be present in principle from an effective field theory point of view, and dimension 8 operators of this form. And so all of those operators have effects on that are hopefully observable in a not too distant future through gravitational waves, either through the imprint on the inspiral phase of gravitational waves. When people do that, particularly this one, it has to be the case to have any meaningful effect. You need the cutoff to be sufficiently low so that the effect is sufficiently large. And then that means that, in fact, the effective field theory breaks down before the merger of the two black holes or the two objects. So you only can describe it for part of the inspiring phase, and then you have to stop and then assume that something else comes in. People have also looked at the effect of those operators on quasi-normal modes, and nowadays, haven't put any reference in here, but people are looking at connections between the signs of the quasi-normal modes and the signs of those coefficients that you would expect from the flow from the UV to the IR. And there's also waveframe constraints, and there's constraints also on the bending and for black hole shadows from the different corrections of the effective field theory of gravity. So let me stop here. I'm not going to go through the rest. And let me just stop by here. Maybe the effective theory of gravity provides completely agnostic without being biased on what kind of UV completion that you want to do or you want to have. It doesn't even need to involve fields per se in the UV, but assuming more a notion of fundamental Poincaré invariance, because any breaking of Poincaré invariance one would expect even at high energy to have some imprints at low energy, which may potentially be have implication in standard model, and gamma ray constraints on breaking of Lorentz invariance are going to very, very high energy nowadays. So assuming Poincaré invariance and assuming unitarity, we can come up with a quite general low energy effective field theory for gravity, which is expansion in different classes of operators. We would expect typically those operators to be extremely suppressed, but they could provide us a window of opportunity to connect with unknown sectors, in particular with the dark sectors, which would only connect through those curvature operators. For dimension 6 operators, which are the first one we would expect to observe, the scale at which they would come in would have to be tightly linked with the scale of SUSY breaking in dark sector, because if you have SUSY preserving operators, the contribution to that will be 0. And in writing down the effective field theory for gravity, one of the main contribution that comes in is the contribution to the cosmological constant, which I haven't even written down in here, which still hasn't been addressed, and in itself is not an issue about the UV completion per se, but already an issue with understanding how the loops of the standard models should contribute to the cosmological constant. And something I haven't written down in here, but we can derive from this procedure already the species bound, where at a given scale m, we know that the number of fields living in there has to be bounded by the Planck scale, otherwise the contribution to the new renormalized Planck scale will be too large. And I'll stop here. I think sorry for running out of time.